Good morning, everybody. Thanks for making it back to the audience after the coffee break. My name is Vitaly Kamluk, and today I'd like to share some of my experience and some of the things I learned on the course of starting your own IoT research. So, yeah, maybe before we start, let me explain who am I. You might have seen me around. In Singapore, I've been presenting a few times. I always come with a trouble to a conference. Don't worry, it's not a trouble to yourself, it's trouble to myself. And this time is not an exception. Usually it is somewhat complicated demos that I do. Not everything goes as planned, as you'll see today, fortunately, but I hope that will still be useful. So Vitaly Kamluk is my name, and I'm principal security researcher. I've been in the industry for quite a long time. I'm based in Singapore for the past 10 years. I started working after I graduated from university. I started at Kaspersky, where I spent 19 years this year. And I still am with them, but I did also spend a couple of years working with Interpol here in Singapore. As you know, they have opened the office in 2014 officially, and I've been there part of the digital forensic lab and cybersecurity researcher, helping with some malware-related cases. I'm passionate about reverse engineering, about digital forensics. I'm running trainings on various matters, including like iOS forensics, malware analysis, threat hunting, and so on. And I recently started my own consulting company, so I'm a contractor now. Now, why are we here? And what do we want to learn? And what's the purpose? What's the objective we are trying to pursue? First of all, when talking about Internet of Things, the IoT field, it's huge. Like, think about these numbers. These are just estimated numbers of how many IoT devices are out there. There are more devices than humans on Earth. So 30 to 50 billion devices right now. And that's a huge attack surface. So it's a huge opportunity as well for the researchers, for attackers and defenders to work in the field. This is why the core motivation, because it's it's even bigger than the number of probably personal computers out there. So we really need to focus on that. So it's part of our research objectives as a research team. But also for me personally, it was a new experience because I'm a software guy. I've been always working with malware, reverse engineering code, and I never really touched the hardware field. And although I come from IT, I have an IT education myself, but it's not like microelectronics or anything. And this is where it was very interesting experience for me, because I think that experience brings you an opportunity to find new security flaws in the system design, possible privacy violations. If the devices are kind of a black boxes, that they do something that they are not transparent, they never publish their code. So for the researchers, it's an opportunity to find some of those, look into those dark corners and find what's happening there, whether this is a trustworthy, a good vendor or not. And then another opportunity that I saw is creating a honeypot. Once you understand how the design is built for a particular device, you could try and implement this virtually. Maybe try and virtualize it, put it in the virtual machine, try to satisfy all the conditions, and then run a simulation of the same device, not only for potential vulnerability research, but also for the honeypot thing. So making it exposed to the internet can actually bring you some of those internet scanners and crawlers that will try and hit your device, and then you can extract something useful and see what's going on from perspective of cyber attacks in the field. Now, how do we even approach the field? Like, how do we start? Well, first of all, you need the device itself, a subject device that you want to focus on, and that's of course a core matter. So you have to choose wisely what you buy. In my case, I did go to Lazada store because I live in Singapore, and I searched for like popular network routers and then CCTV cameras, like home security cameras, things like that. So I found this camera called TP-Link C100. And here I'm quite vendor agnostic. Normally I don't really promote or pitch or don't attack any particular vendor, but this was just affordable and very popular. According to feedback, people were happy, and it was kind of a cheap device to get and play with. Good for starters. So this is how it looked on my desk, and this is where research began. So what do we want from such a device is usually try and understand, well, how it's built to extract the code. Now, the device comes with certain features that may help you run this research. Normally, these devices will be connected to a network or at least accessible through Bluetooth for initial configuration, and so was this. It's a smart network-capable device. It came both with Wi-Fi and Bluetooth. And the way you configure this, normally you install the app. The app uses Bluetooth for initial pinging of the device, and then once they agree on Wi-Fi network configuration, you can connect over Wi-Fi, which is faster, of course, more reliable, and covers wider range. Now, this particular device also comes with a SD card slot, which is handy because it's an external storage you can plug in. Think of this as a USB port in your computer, right? So the cameras normally don't have USB ports, so you don't plug things in such IoT devices. But it does come with an SD card. That means it can read something, it can process, or potentially exposing vulnerability surface, but also useful even for analysis, because some files may be stored there. You can pick it up and analyze, see what's there, what device tells about itself, maybe diagnostic logs can be dumped there, and so on. Now, like I said, it is operated from the app. So the app has to be installed on your smartphone, and you better have a root control over that smartphone so that you can kind of instrument the app and see what is happening. But yeah, this is the way how they build it for consumers. You install the app, click a couple buttons, synchronize, let it connect to your Wi-Fi network, and then boom, you have a live stream from the camera. Another important point was a factory reset button. Very handy. Normally, most of the consumer devices are built with such a button so that if something goes wrong, I don't know, it gets stuck during the upgrade, or maybe it just gets stuck because of the bug in the code, or perhaps it hangs on trying to reconnect to Wi-Fi. It's always useful to reset the device, not just power off, but reset the factory settings so that it recovers the original configuration. Then this particular device, of course, because it's a camera, it does come with a microphone and also embedded speaker, just in case you want to interact with somebody near by the camera. So these are features, these are sensors, these are input and kind of channels, the way you can interact with the device. I'm not sure if you can hack a device through microphone. Probably it will be next level presentation. Well, every input counts, to be honest. Every input you have to explore as a security researcher to see if that can be leveraged in order to get a hold of the device and the code that is running. Now, this is our main objective, to acquire the firmware from this device that we just physically have. And how do we approach this? The first approach that I thought of as a software guy was, well, let's see what's happening on the network. Like, how does it communicate? Maybe it can expose some of the secrets. Maybe I can scan some ports. I can find some backdoors. Maybe there are some default passwords. Maybe I can even brute force some of the credentials. Or maybe some of them are known. Maybe vendors hard-coded them. So this is what you do first thing. You kind of explore the network surface here. And the original network map, when consumers are using this, it is pretty much like this. So the first step, like I said, you connect over Bluetooth, you find that device, and then the app transfers the basic settings for the Wi-Fi that you want this device to be connected to. So you basically provide your credentials from the home or office Wi-Fi network to the device, and the device stores the SSID and the passphrase from the Wi-Fi access point, and then it keeps it on the device so that it can connect directly, and you may actually leave your home and you can still, of course, get connected to the CCTV camera from anywhere where you have internet. So it does make sense. So this is channel number 2. So you see the camera connecting to the Wi-Fi router, and then you independently somewhere else or at the same place connect to the internet, and you interact through the cloud infrastructure that is provided by the vendor. Now, in order to analyze the traffic, what is happening here, you can see clearly there are channels that you want to intercept and see what communication is happening in each particular case. So whether the device to smartphone communication, whether it is a device to the internet, to the cloud communication, or your smartphone to the cloud communication as well. So everything matters. That's why you really have to build your own network map. So this is how it looked roughly in my case. Well, I did use a Raspberry Pi. That's a cheap, affordable, kind of universal solution. You can run your own access point. You can pretty much do your network routing and make sure that all the traffic is intercepted. You can install things like at the real, you can try to run SSL strip or mitten proxy and try and remove the layers of encryption from this communication, which is very helpful. So this is why instead of letting the camera connect to my real Wi-Fi access point, I provided credentials from the fake access point that was run from the Raspberry Pi. So I did the same to connect my smartphone to it, and well, then I relay this to the real Wi-Fi router, which also used some VPN exit nodes, just to make sure that there's nothing funny happening from the vendor side. Let's say if they blacklist my IP and then they blacklist my home, I never can continue. So as a researcher, I'm just a bit cautious, and I would rather use a different kind of external IP that I can replace. Also, it's useful to check whether the traffic is the same for different countries. For example, maybe for Singapore, there's a little bit more telemetry collection comparing to some other countries. So it was useful to have such an infrastructure. So that's what I recommend for all beginners to do the same. So first thing I noticed there when I just tapped the traffic was a number of broadcasts that were sent by the app, and the camera responded. Those broadcasts were UDP based, and then they just transferred it was an awareness broadcast saying that here you have to connect to this server, and then communication took place over HTTPS. So they use REST API, so it was SSL protected. However, although they used SSL, of course, they couldn't really encrypt all of the traffic because the communication, for example, between the camera and the app couldn't be fully protected. Why? Because, well, for that you need to have a certificate authority, a proper certificate installed on the camera, which cannot be really validated because it's just a peer device in your home network. So they couldn't use proper certificate. They wouldn't risk to put it there. So they use self-generated certificate for the app-to-device communication. So this is where you could actually remove with tools like mitten proxy and then see the plain HTTP traffic, which was very handy. However, communication between the device, between the IoT device, the camera and the cloud was properly protected, and so was the communication between the smartphone app and the cloud infrastructure. Well, with the smartphone, you can probably do something such as instrumenting and then removing SSL pinning, like replacing certificates with your own. So you can do a little bit of magic there and tap into communication between the app and the cloud. But of course, it doesn't bring you closer to the secrets that are shared between the camera and the vendor's cloud. And this is what we are mostly interested in. Just to show you how it looks. By the way, like when you initially set up the device, there's some default credentials being used, like admin, but that's for a very short period of time when they initialize the device, and then they use session token and they update those credentials. So it's just for a short window of time. That's not very helpful. So you cannot really access any device like that. So it's not long-term security vulnerability. But if you're lucky, you can possibly tap into that. So you can send some some instructions and some functions be called over the REST API, if you know of course, API contracts. Now, this credentials update is happening, but another thing that I noticed was a command that was pushed from the mobile app to the camera, initiating the upgrade of the firmware. So it first asks the device to go to the vendor website, to the cloud, and check if there are new firmware available. And if it's available, it offers the user to do the upgrade immediately. So if you initiate that, and that's through the API calls from smartphone to the camera, then the device, the camera, fetches the firmware file, the archive, unpacks it, and then self-upgrades. And this was already interesting because we now dealing with the firmware. If we could intercept that firmware transfer, that would be great because it already reveals the code that is running on the device, right? So it's one of the approaches. Now, this is exactly what happened. Luckily, they even didn't use HTTPS to fetch the firmware. There were no authentication used. So basically, once I initiated that function, I called the function like to upgrade the firmware. I've seen plain HTTP traffic going to the cloud, fetching the firmware binary, and then doing the upgrade. So I thought, bingo, we can deal with that, and I can just focus on analyzing the firmware itself rather than trying to poke the device further. However, this is how it looked. The bin file, it was an encrypted blob. So this is how it looked, hex dump of the blob. Now, I didn't realize immediately it was encrypted. I thought maybe it's a kind of proprietary format or something, but clearly the entropy and there was some header in the beginning, but the rest of it was pretty much packed or encrypted. And yeah, later I have confirmed that they've switched from unencrypted firmware upgrades to encrypted. So the device fetches the encrypted firmware and then decrypts it using the key stored only on the device that I'm not aware of. And then it does self-upgrade. So that's a bummer. And they did this just after I bought that device. Basically, the previous version was still using unencrypted blobs, and this is how it looked. I found some people actually posting the archives of the previous blobs like that they intercepted. And yeah, clearly you can see a bunch of zeros in the bottom. So it's same file, almost same size, but clearly not encrypted with some plain text in there. So bad luck, at least, with this. So I moved on, and I found that actually there's a function for firmware downgrade. And this is something probably common for some vendors or some devices. So you have always to consider that fact that if, let's say, a consumer device gets a broken firmware or something is wrong, the vendor may want to, at least through technical support, explain the customer how you can, get back the previous version. So there was a way to downgrade the device. So I thought maybe if I take this non-encrypted version of the firmware and I initiate the downgrade procedure, at least I can have the device that runs the code that I have a copy of, and I can focus on my research, like how to get into the device. So for that you needed an SD card. So there's a little bit of magic involved. So you need to have this knowledge in advance. And you can get it only from analyzing previous versions that were not encrypted. Through the scripts that they have, they did check that device, you plug the SD card, you plug has two FAT partitions, so they go to the second partition and they fetch a file that is, the name is hard-coded, it's factory app.boot.bin, and then you can, if there is such a file, they will try and validate and do the downgrade. In my case, unfortunately, it didn't work as well. Why? Because there are slight differences in hardware, let's say, profile of these cameras. So they are released with different profile for different countries because of, I guess, maybe regulations for wireless communications or some other regulations. So the one that I had, it didn't match. So the unencrypted blob I had of the firmware, it didn't work in the device. It just refused to reflash. For this matter, that was a difference in the hardware profile. You have to have exactly right firmware file that is non-encrypted to be able to do the downgrade. Well, maybe for some other devices and vendors, it may be not the same. So you have to still consider this path of the downgrade. Next, after network interception, I decided, well, I kind of explored all the options. I scanned the ports, of course. I tried to look into the protocol. There was nothing really useful. The API contracts didn't help. So I thought I should go, the hard way or the hardware way. Well, it is hard for me because I'm a software guy. And the hardware way was as following. Like, you have to physically disassemble the device without breaking. I wanted to put it all back in one piece. And then you disassemble and start exploring, like, what is there. Of course, there is a PCB inside, and then you have to explore what's on the board itself. Now, part of this is identifying components that are used to make the PCB work. So right now, I'll say I did this research last year. So right now, I would probably rely on some of the interesting features of OpenAI ChatGPT to identify parts. I've seen reverse engineers using that, because it's now multimodal. But you can actually feed it images and ask for identification of particular chips. It's very helpful. You shall not really neglect this. But even with your own eyes and magnifying lens, you can identify some components. So here, for example, you just read what's written on the top of the chip, and then you start doing your online research using the search engine, and then you can identify that, well, this probably is a wireless chip that is Wi-Fi and Bluetooth at the same time. It comes from Realtek. So I kept looking for the memory chip that I wanted to find eventually. So this, for example, this is a sound amplifier here. And they're all tiny, of course, so you have to really gear up with a good magnifier lens, and this is a frequency oscillator. So there are some other less relevant parts. And I tried to find the memory chip. It just wasn't there. It didn't have memory, which is not possible, right? So the biggest component was a system on chip, the SoC from Nginx. So it's kind of a CPU and a RAM and a possible embedded firmware there. So the multifunction kind of whole system consistent of multiple ingredients. So, but it's not where the firmware is stored. Firmware should be stored on some sort of a storage, like an equivalent of a hard drive in the PC, if you think of that. So it has to be a memory chip, in particular flash memory chip. So I kept searching for that, and really it wasn't there. So eventually I found something that was just below the lens. So I don't know if they did this intentionally or not. They just kind of covered the chip with the lens. So if you want to get there, you have to deal with removing the lens and exposing the sensor matrix, which is very sensitive, of course. Like any dust or scratch can spoil your quality of the video. But once I did that, I removed the lens. I found that there is actually a tiny chip sitting just below. And I identified that it was like 8 megabyte memory chip by, again, looking up the name and the model that was written on top of it. I found some specifications. Typically, the producers of microelectronics, they make specifications of their chips available, so you can go to the website or just look for some mirrors of documents, and then you find white papers describing the chip and its capabilities and so on. So once I did that, that contained, of course, the firmware I wanted. Now, how do we get it off the chip? Well, you have to deal with the chip. You can try and even extract it right from the PCB, which didn't work in my case. So the hardest way is to desolder the chip, which is super tiny. It has like 8 pins, but it's super tiny, and using a regular soldering iron can actually be very troublesome, especially if you want to reassemble it back. So I invested a little bit, it's maybe $150 setup or something, with a kind of cheapest available equipment that was there. I bought, and this is not just a soldering iron, but a heat gun that blows with a very hot air, and it allows you to unsolder things much easier. And you can control the temperature so that you don't really burn the chip. Now, if you desolder the chip, then next step is to dump the memory of that chip. And how do you do that? Well, again, it's a microchip. So the scale is like this. So if you put it on a ruler, it's like half a centimeter. And you have to attach to these 8 pins here, carefully, independently, and then try and interact with this from a PC. So yeah, of course, there's special gear for that, which is a contact clip that I purchased, super cheap, and that is designed for particular shapes and form factors of the memory chip, so it has to be compatible. So once you fetch the specification for the chip you're dealing with, just look it up and make sure that you get the right clip, and then you can clip on the chip and deal with memory dumping process. So how do you dump memory from a chip once it's unsoldered? You got to have a special additional device here, which is a flash dumper. It allows you to dump memory, to interact with memory chips. You can also reflash it back, so it's a read and write operation, which is useful because you can experiment with the firmware, put it back, and then, well, every time you have to solder it back on desolder if you want to reflash, unfortunately. So it's not very handy. However, in my case, I wanted to get the firmware first and then deal with that. So I used a hardware known as TiGuard. It's kind of, there are plenty of different other variants of, let's say, memory dumpers, but this is like the most modern, coming from a friend of mine, Joe Fitzpatrick. And that is known for hardware hacking trainings and gear. So they are making their own. And this one is universal, so it does work not only with one type of memory chips, but also helps you to deal with all kind of IoT-related research. And it does come with a USB-C port, so you plug it there. Then you can connect the pins of the chip through the clip to these pins on the TiGuard device, and then you can interface with this from your PC. Now, just running some commands, basically a single command, if you connected everything right in the correct order, will get you an 8 megabyte file that will contain the contents. It will have the contents of the flash memory. So this is how it looked in my case. A little bit of header here, and then a bunch of zeros. It's not the same as the firmware that you've seen previously in a non-encrypted form. Why? Because it's already unpacked. So the one that we get from the server of the vendor is more compressed, and once the flash this file on the actual chip, it can be put into different positions. That's why there are some gaps resulting in these zeros. Now, all right, so once we got the memory, how do we get the shell? Because shell on the device is somewhat very useful, especially for debugging, to see how it works, maybe for potential interception of network communication. Again, replacing some certificates would be nice. So one way to get the shell is to reflash this SPI memory chip. By reflection means like you have the dump of the memory, right? Then you can tamper that. You can probably modify files if you read the file system, or do some tampering with the firmware that you saved from the chip, and then you could put it back. If you do that, it's a possibility for sure, kind of a last resort, but be mindful that there are some integrity checks that are happening, so the device may get just broken, and you can keep reflashing. And every time you reflash, you have to solder it back and then unsolder to do the same operation again, and then it's just how kind of experience. So you probably don't want to go that path. However, it's a possibility if you're absolutely certain about what you do. The other possibility is so-called UART console. It's kind of a serial connection to the device that is left by the engineers, by the developer of the device to test the device if it's in a working condition, if everything is fine. Like it's basically for QA, quality assurance, I guess, matters, and development as well. So they often leave pins from this interface that connects directly to the system on chip, the SoC, and that allows you to interact with the device in a more organized fashion, so you can have actual console, pretty much like you're attaching a display to the device. So over this serial communication, you can interact in a text form. So you can type commands to the device will reply. But the challenge with this device was that this UART console, normally it comes with pins that are marked on most of the consumer devices. If you take network routers, pretty big PCB boards, and they normally have not just numbers, but even names written on the boards. In my case, there was nothing like that. So I looked and looked and looked. There were some numbers, like cryptic identifiers that were alphanumeric, but they didn't really explain what they meant. So there was nothing that looked like a UART pins, and that takes 4 or 6 pins, depending on the configuration. So I tried and brute force all possible pins that I saw there. I tried to kind of deduce, like, where is this UART? Does it even include UART? Because previously it was there on some older different variants of the same camera. They actually had it marked, but on mine was no sign at all. So eventually I found on this image, on the right image, on the top, you can see 4 pins aligned at the very top. So this was my guess. It must be UART, maybe. So how do you check that? You have to try. But to be able to interact with this, you have to know exactly what each pin means in order to connect to Tigard and then interact with this. So brute forcing all possible 4 combinations could result in potentially burning the device, breaking it. So it is not recommended. So you have to really identify the pins. And there are techniques that can help you do this in an organized fashion, I would say, in a more systemic approach, scientific. Deduce what these pins are, starting from the ground. So you basically need a multimeter for that. And then the ground is identified by, you connect to the candidate ground pin, one of the 4. And the other the other cable has to go from the multimeter. It has to go to the ground, which is confirmed. Like basically, it is on the power plug, the power barrel that you plug the cable in. There's a ground on the outside. So then you switch the multimeter to a continuity mode that shows like whether there's 2 points are connected, whether there's a circuit without any blocking, and of course we're dealing with a powered off device, so it just checks the continuity of that path, and if it exists, that is the ground pin. So that's already something. Second, you can figure out where is the voltage, the VCC pin. For that you have to power on the device and then switch to the voltmeter and then you can measure the voltage. If it's steady, if it's 3.5 volts, then you're probably dealing with the right pin. But different devices, they have different powers, so the voltage may vary. But it has to be a steady supply of the voltage through VCC. So, okay, once we figured where is the VCC, now there's just 2 left, RX and TX. You can pretty much try and guess it to just 2 combinations, right? But to do it more in an organized fashion, you can again use the voltmeter check the voltage fluctuations. If you connect to there are 2 pins, RX and TX, for receiving and sending data. So it's kind of two channels, receive and send data to the device. So when you boot the device, it prints something on this port, like printing on a display if it's a computer. So the boot process will generate some noise. Some text messages will be printed to this interface. And if you connect the voltmeter to I think the TX, and this is where it starts, you will start seeing some spikes locally, like they will be changing, fluctuating signal. And that means this is a transmission, it's a TX pin. So the rest is just, of course, remaining is RX. And now that you have deduced the scheme, you can use that to connect the cables to these pins. You have to solder them carefully. That's what I did. And then these 4 cables will be attached back to the Tigard. Again, it's not only useful for dumping memory from the chips, but also to interact with UART. So there's an interface for UART. And then the USB-C cable goes into laptop you start a terminal application such as Minicom, and then you basically get a terminal, a console of the device itself. Now, here is the tricky part. And yeah, as you see, like I didn't come with normal PowerPoint slides, and I always come with trouble to myself, and this was a trouble again. I was hoping to show you a live demo of how we can get root on the device itself, but let me show you what happened to me. I haven't brought the whole setup to connect and show you live what's going on, but there's a little bit of a trouble. So yeah, this is just a moment. So yeah, this is Tiger turntable here. Let me rotate it. Which side? This side. Yeah, unfortunately, you can see I had an accident while bringing this thing. One of the pins, unfortunately, got it cracked somewhere on this side, and I no longer can really have a stable connectivity. So it's not probably the proper environment to show such demos. You have to do this in your lab. So I don't have a soldering iron with me, and I think it badly cracked because I think it's missing some part of the metal on the PCB part. So I think I pretty much wasted this one, unfortunately. But yeah, the demo was about basically showing you the Minicom terminal on Linux that allows you to see the booting process of the boot process of the device itself, and then let me quickly jump here. It was showing the boot process of the device, and then you can interact with the device by basically using your terminal and the keyboard. The idea to get root and to get shell on the device is as following. Like there is normally a bootloader that is used on most of these consumer devices. Some of the most affordable open source are called U-boot, and that one can be used. It's kind of a pre-system shell that allows you to interact and change settings of the booted system. And what device has on the firmware is a mini embedded Linux. So if you can change the boot options of the kernel of that Linux instance, you can pretty much do the single user mode. You can pass an argument to run a shell for you, and then you can change the password of root in the RAM, because everything is kind of stored really in a non-volatile memory. So the original settings that are taken during the boot are from read-only memory. So once you change the root password, you can continue booting the whole system, and then you can have credentials, and you'll log in through the same serial console. Because if you don't do the password change, if you don't reset the password, you will see the login prompt, like on regular Linux, but you don't have credentials. They are not known to you. They are set by the vendor. They encrypt it, like you can try and crack the hash. You can extract it, of course, from the firmware, but I guess that's pretty long enough. So I tried doing that, didn't work. So it was not an obvious password. But playing and messing with the bootloader, U-boot in this case, did really help. So in case of this particular TP-Link device, they also protected the bootloader from possible, tampering by the researchers, I guess, or strangers. So in order to make it interrupt during the boot, you have to press secret combination, transfer secret combination of keys, which is stored in the firmware itself, so they could be reverse engineered and extracted. So they just wanted 3 keys to be pressed, like SLP in this case, and then they would provide you with the boot pre-boot prompt that can be used to interact and then change the boot options of the kernel. Now, what is next after you have the shell? Of course, you can run privacy sweep to see how is your Wi-Fi stored on that device. Is it being transferred to the cloud, to the vendor? Do they know about this? Like how much else information is transferred to the cloud? For example, I found that they're transferring like network names from Wi-Fi, neighboring Wi-Fis to the cloud for some reason, but not my password at least, which was fine because it was a research setup. Then you can even work on further firmware decryption because now you have access to real running system. You can initiate upgrade, you can debug the process, you can see which encryption keys are used and what is the format. You can really not just do static analysis, but do dynamic analysis through a running a debug server right on the device. Although that's MIPS CPU and their architecture, so be prepared for that. And then eventually you can even try and virtualize the firmware once you understand how exactly it works and what are the requirements to initiate the device in the working stage. Now, again, the presentation was more about how to start doing your IoT research. So once again, important points is choose your subject wisely. Get the most popular hardware, something you can replace. You see, I just destroyed one, I guess. I have to get a new one, probably, or try and solder it back, see if it works. So it has to be recent products so that it has impact, so they're users, not just a rare device that nobody really wants. So you want to invest your time into something mainstream. It has to be inexpensive, be prepared for replacements. And yeah, gear up. As you've seen, I bought something on the go. I started from complete zero. I wasn't a hardware guy, so I bought everything depending where I navigated. And be prepared that mistakes happen. It's not just these cracking pins or cables detaching, but also at some point, I took notes of every step, and this is what I recommend you to do as well. Take notes of every of your steps so that you can reproduce it at any point of time, return and reanalyze. So I did exactly this when I was soldering the chip back to see if the camera still works after dumping the memory. I did according to my instructions, but I was probably not focused enough. So I put it, and then I started the device. It didn't work. It just made some buzzing sounds, like to the speaker, like bzzz. And I thought, well, that sounds bad. Probably I'm bad in soldering. And eventually I figured out that, according to my notes, I confused, the up and down of the chip. So it was actually soldered upside down. So luckily, it didn't burn the chip or the system. So I unsoldered it and soldered it back properly. And it kept working. Fortunately, I can't show you today, but it did work without any issues. So mistakes happen, be prepared for that, and try to learn from others. And this is why I'm here, to show you my path and invite you all to this wonderful world of research in the IoT. Well, with this, we are pretty much are out of time. Thank you very much for your attention, and sorry again for no live demo today. Thank you.
Okay, now we can open the floor for some Q&As.
Hi, thank you for your talk. Just a quick one. Why did you need to desolder the chip if you have a shell on the device? What was the purpose of the soldering?
So, there was one of the main objectives is, of course, to get the original firmware, so you can focus on static analysis and software analysis. I wanted to move from the hardware domain to the software domain as fast as possible. That's first thing, so that you can have exactly the same firmware and then work with that, extract the secrets potentially, and then see what can be done on that front. Because at that time, I wasn't even sure that I can get the shell. So it was the next stage. Because once I got the firmware, I extracted things. There was some, lack of clarity. It's a MIPS CPU after all. Like reverse engineering that is a bit hard and new to me as well. So I thought, well, with reverse engineering, you can pretty much boost your speed if you have a dynamic kind of approach at the same time to the static. So if you have a debugger and the static disassembler, it is much, much faster. So this is where I started looking like, how about the live shell? And I found that, yeah, there is a possibility. But yeah, it took some time to get it. But generally, like if you're top pro, then you can pretty much focus on static and do such things statically. Maybe it can be even easier, like if you, let's say, extract the hash, it's crackable, then maybe you can get a shell over the network, because it does expose some protocols, you just don't have the credentials. So yeah, it may work even with just extracted firmware in your case. In this case, it did require me to get the shell over the USB. So after that, you have the shell. You can enable, telnet, SSH, whatever you want, reset credentials, and connect over Wi-Fi, which is much more convenient. So you detach the USB cable. You no longer depend on the UART, and you can do whatever you want with already started device. And yeah, also you're not spoiling anything. So if you mess up, if you delete some important binaries, if you mess up, you just reboot the device, and it's in the clean state with the original credentials, the original settings preserved, because there are no changes to these IoT devices done permanently. It's hard to do that. You have to really reflash some of the special partitions, configuration blocks that are not stored on the same place where the system is running. System is running in RAM mainly. Yeah, I hope that answers your question. Any other questions?
Hi, this is just out of curiosity. During your course of doing this kind of research of IOC, so probably you will be downloading a lot of firmware. So how many percentage of firmware actually out there that, based on your experience, that actually is encrypted versus unencrypted? And if they are encrypted, like, have you ever tried to see whether this is very simple XOR, or is really how do they encrypt it actually? Do you have some insight on that you can share? Okay. Thank you.
Well, the encrypted firmware is not widely common, I would say, but some of the top vendors, like I guess TP-Link would be one of them, they are just switching to encrypted firmware to prevent any kind of easy vulnerability hunting. That's a problem for security researchers for sure in the first place. Yeah, I think Apple did the same for iPhones initially, right? They encrypted their firmwares, and then, well, they realized they don't want to do this because of performance issues. They switched to non-encrypted firmwares after some time, but it's been around for, I think, more than a decade, I guess. But most of the IoT, they are running kind of a low performance and low power, systems. The CPUs are not as powerful, so they try to save on such things. So naturally, they will not overload system with additional encryption. But the general trend is that there will be more and more encrypted firmwares. I can't tell percentage, like how many of those billions are using encrypted firmwares, but I think we have to be prepared to deal with that. And the way to deal with that is one of these approaches that I showed, like either interception of the firmware when it upgrades, or downgrade of the firmware, and then trying to get some sort of understanding of how it is encrypted. By the way, in this case, your question was also about the algorithm, how they do this. It's not just a simple XOR. They use a proper, full suite of encryption algorithms, like relying on AES. And yeah, it's a bit like you don't guess such things. Like trying to guess XOR key is one thing, but yeah, dealing with AES key that you don't know, it's not the way, I guess, to try and brute force if you have an encrypted blob. So you really need to have more reliable approach, just like I showed. Maybe that will help you in your situation. Yeah. Any other questions?
All right. We have time for one more, and here on the left.
Thank you very much for your talk. So I have two questions. So first question is about how do you detect a sensor whether it's spying on you? So because previously there are chips on the motherboard, on a PC, for example, which is actually designed to spy on all your activities. So it's about detection. The second one is how do you add a sensor onto your mobile device, for example. So something that which I actually wanted for a very long time is a smell sensor, so which is not much spoken about. So have you done experiment on this subject? Thank you.
Starting from the first question, how to identify that device may be spying on you? Well, it's one of the objectives of this research is to figure out, like, is there any privacy violations or not? Like, should we trust the vendor, like, or is it a credible one? So this is what we all shall challenge, really, like, and explore, like, what devices are installed, what cameras maybe you are using for your own purposes at home, or what network routers or network attached storages, like, what they do they interact with your network and all. So the only way, a reliable way to see whether the spying is happening is, of course, you need to look into the communication of the device itself and the vendor. So if there's no communication happening, it is unlikely they will ever get this data unless they come with physical proximity to you and do some secret wireless transfer, which is unlikely when you think about consumer devices. If you are a special target, let's say if you're a high-profile target, maybe a VIP or a politician, that may happen for sure. But again, it requires interaction. It requires some sort of traffic to be generated. So for such devices, well, the hard way is to reverse engineer and understand all of its capabilities, when it transfers, under which conditions it can transfer some information. Maybe it's once per year, then they beam it out, and that's it. Or maybe they maintain constant connection to the server infrastructure, and you can easily spot that something is happening. So you need to tap into that communication and see what is being transferred, whether this is sensitive information, whether they collect more than they really need for this device to function. And then, yeah, that's the best way to spot. And what I do by default when I connect devices to my home network, well, first of all, there's a separate segment for devices that I don't trust necessarily 100%. Then I can pretty much, control and block all communications from these devices. So bypassing that probably is hard to kind of anticipate by the vendors, so they are not prepared for any kind of bypass and extra channels that are kind of out of band. So you can easily block such things. Even if it's a spy device, it will be useless because it won't be able to communicate with the master. And I didn't really follow your second question about the smell sensor for the device for mobile phones, or did I hear it right? Can you please repeat the second question?
Yeah, it's about smell sensor, which is not much discussed in general. So you can actually tailor-make a smell sensor. I know at least from Grenoble, they do all this kind of thing, or from Israel somewhere.
That's amazing.
But to activate this, either you build an external device with this sensor and connect to your mobile or PC, and then you activate this smell activity, which is not very difficult. But to connect it and make it functional, something which I would like you to explore.
Thank you.
Thank you very much.
Thank you. Thank you for coming to my presentation and asking the questions. I'm not familiar with the smell sensors, to be honest. Sounds like pretty much futuristic, but yeah, excited when it comes, when we can smell people. It's interesting. Like, you smell, if it smells like your subject of spying, then you activate certain transfer. That would be an interesting combination for sure. But that is the future, I guess. Thank you, everybody, for your time and coming to my talk. Enjoy the rest of the conference.